Hey everyone, and welcome. Today we're diving into something called Tucker decomposition. Now I know, it sounds a little intimidating, but stick with me because we're going to make it super simple using a really fun analogy, finding the hidden recipe inside your data. All right, so let me ask you something. Think about a video clip, maybe from a security camera. It's really just a ton of images, one after another, right? How in the world does a computer look at all of that data and figure out what's actually happening? The important stuff. Well, the secret is all about how we deal with data that's, more complex than you might think. Most of us are used to data that looks like a simple spreadsheet. You've got your rows, you've got your columns, easy peasy. But here's the thing. A lot of the really interesting data out there, we're talking videos, medical scans, you name it, it isn't flat at all. It has way more dimensions. It's not a sheet of paper. It's more like a whole cube of information.
Okay, so if we can't use a flat spreadsheet, what do we use? Well, we have to think bigger. We need to go beyond the spreadsheet and into what we call the data cube. All right, so the fancy mathematical name for this thing is a tensor. And yeah, the official definition can get a little abstract. But honestly, the easiest way to wrap your head around it is just to think of it as a data cube. That's it. Instead of a flat square, we've got this rich, multidimensional block of info to play with.
Okay, so we've got our data cube, great, but a giant block of raw numbers isn't super helpful on its own, right? We need to figure out what's really going on inside. And that brings us to the whole point of this explainer. We're going to find the data's recipe.
And that's exactly what tensor decomposition is all about. It's the process of taking that huge, complicated data cube and breaking it down into its simpler, more meaningful parts. Seriously, it's like being a master chef who can taste some complex sauce and tell you exactly what ingredients went into it and how to make it. Now, there are a few different ways a chef could do this, a few different techniques, but the one we're going to focus on today, the real powerhouse method, is called Tucker decomposition. You can think of this as our master chef's secret, most powerful technique for reverse engineering the recipe from any data dish you throw at it. So here's the recipe formula in action. It looks a little mathy, but it's super simple with our analogy. On the left, you've got T, that's our tensor, the final dish we're trying to understand. And on the right, those are all the parts of the recipe. G is what we call the core tensor. Think of these as the main essential ingredients. And the A, B, and C, those are the factor matrices. They're the mixing instructions. They tell us exactly how to combine those core ingredients to get our final dish.
Okay, but wait. How does the algorithm actually find these ingredients and instructions? I mean, it's not like it can taste the data, right? Well, it uses this really, really clever move that I like to call the unfolding trick. So here's the problem. We can't really analyze our 3D data cube when it's all stacked up like a block. So the first thing we have to do is flatten it out, kind of like rolling out a big piece of dough. In the biz, this is called unfolding or matricization. And all it really does is turn our complex data cube back into a simple flat spreadsheet, or a matrix, which is something we already know how to work with. Here's how it works. It's actually pretty intuitive. First, you start with your 3D cube. Then, you slice it up along one of the dimensions. Imagine slicing a loaf of bread. Step 3, you just lay those slices down one next to the other, side by side. And what do you get? A single, flat matrix that has all the original information, but now it's in a form we can actually analyze. Pretty cool, right? But here's the really clever part. We don't just do this once. We repeat this whole unfolding process for every single dimension of the data cube. So if we have a 3D cube, we do it 3 times. We end up with 3 different flat views of the same data. Each one gives us a totally unique angle on the hidden patterns inside. All right, so we've done all this slicing and unfolding, and now we've got these flat matrices. So what? What do we actually do with them? Well, this is where we finally find our ingredients and instructions. Okay, for each one of those flat matrices we just made, we bring in another really powerful tool. It's called singular value decomposition, or just SVD for short. You can think of SVD as like a special kind of magnifying glass. Its job is to look at that flat data and pull out the most important, the most dominant patterns and trends. And those patterns, they become our mixing instructions. And those instructions we just found, that's what we call the factor matrices. Remember the A, B, and C from our formula? This is them.
Each one of these matrices basically holds the cheat sheet for the most important patterns that we found along one specific dimension of our original data cube. So after we pulled out all the instructions, the main patterns, what's left over? Well, what's left is the core tensor, our G. This is our list of core ingredients. The crucial thing to remember is that it's a much, much smaller and compressed version of our original data cube. Its whole job is to show us how the main patterns from our A, B, and C matrices all interact with each other. So let's just step back and see what we've accomplished. What's the real power here? Before we started, we had this enormous, dense block of numbers that was really hard to make sense of. And now? Now we have one tiny little core tensor and a few instruction matrices. We've basically swapped a massive data storage problem for a much smaller, much more elegant problem of just understanding the core structure. It's a huge win. Okay, so this is all a really clever process, for sure. But why does it matter in the real world? Let's talk about how this helps us compress our world. And here's the magic trick. We can now use our recipe to perfectly remake the original dish. By taking that tiny core tensor, our ingredients, and combining it with our factor matrices, the instructions, we can actually reconstruct the original massive data cube with almost no loss of information. We've basically boiled down the essence of the data into just a few key parts. And this ability is just incredibly useful. I mean, it's the foundation for so many things we use every day, from basic data compression to really complex data mining. It's especially critical in machine learning. Remember that video clip we talked about at the very beginning? This is how an algorithm does what's called feature extraction. It's how it finds the most important action in all that noise. You know, one of the sources for this explainer put it perfectly. It said the goal of tensor decomposition is to approximate a tensor, thus uncovering latent factors or structures within the data. That word latent just means hidden. So it's not just about making data smaller, it's about finding the hidden meaning inside all that complexity. So think about what we've just seen. We've seen how a pretty elegant mathematical idea can act like a master chef, finding the hidden recipe inside a giant cube of data and simplifying it down to its absolute core. It really makes you wonder, right? If we can do this for data, what other complex systems out there are just waiting for us to figure out their recipe?